In part 1, we've seen how to find the node with a given key in a binary search tree using a recursive solution. This time, let's look at how to do this iteratively. Let's say we want to find the node with key 3. So remember, in the recursive solution, we start at the root node and we check, is 3 equal to 6? No. We then do a comparison to determine whether we need to continue looking in the left subtree or in the right subtree. This time 3 is less than 6, so we would continue doing the lookup in the left subtree by calling the function recursively with root 2. 3 is not equal to 2, 3 is greater than 2, so we would continue with the right subtree. 3 is not equal to 4, 3 is less than 4, so we would continue with the left subtree. And we would find 3, and we would return it. So as you can see, the idea is to start at root and then move to the left when we have a key that is smaller, and move to the right when the key is greater. And we stop when we either find the node with the key we want, or we hit null, indicating that there is no node with such a key. Let's see how to implement this process iteratively. We have again a function called findNode, which takes the root of the binary search tree and the key we want to find, and returns the node with that key. We start by setting the current node to root, and then we enter a while loop. While current is different from null, we check, is key equal to the key of current? And if that's the case, we found the node that we were looking for, so we just return it. Else, if the key is less than the current key, then we need to continue the lookup in the left subtree, so we simply move current to the left. Else, key is greater than current key, so we continue our lookup in the right subtree. If we exit the while loop, this means that current became null, so we will just return null. So what we're doing here essentially, we're saying while current is not null, we check, is key equal to current key, and if it is, we return current. If not, we either move to the left or to the right, depending whether key is less than current key or whether it's greater. And we keep doing this until key becomes equal to current key, or by moving to the left or to the right, current becomes null, so we exit the while loop and return null. Let's run through some examples to demonstrate that this function works. We have the same binary search tree we've seen before, and let's say we want to find key 5. So we call our function findNode, passing in root and the key 5. The first thing we do, initialize current to root. So current is 6. So even though we're indicating that current is equal to an integer, what we really mean is the node that has that integer as key. Then we check, is current different from null? Current is different from null. So we see, is key equal to current key? 5 is not equal to 6. We check, is 5 less than 6? Yes. So we set current to current left. The left of 6 is 2. We go back to the beginning of the loop. We check, is current different from null? Yes, it is. We see, is 5 equal to 2? No. Is 5 less than 2? No. 5 is greater than 2. So we set current to current right. The right of 2 is 4. We go back to the condition. Current is different from null. We check, is key equal to current key? 4 is not equal to 5. Is 5 less than 4? No. 5 is greater than 4. So we set current to current right. The right of 4 is 5. Current is not null. Is key 5 equal to current key? Current key is 5, so this is true, so we return current, which is exactly what we were looking for. Let's look at another example where we want to find key 10. We call our function with root 6 in key 10. We initialize current to root, and we check the condition of the while loop. Current is different from null. We enter the body. If key is equal to current key, 10 is not equal to 6. If key is less than current key, 10 is not less than 6, 10 is greater than 6. So we move current to the right. The right of 6 is 7. Again, current is not null. Key does not equal to current key. Key is not less than current key. 10 is greater than 7, so we set current to current right. The right of 7 is 9. Current is not null. 10 does not equal to 9. 10 is not less than 9. So we set current to current right. The right of 9 is null. And now current is null, so we exit the while loop and return null to indicate that node with key 10 does not exist in this tree. Let's analyze the time complexity of this function. In the worst case, the node we're looking for is not in the tree, and we move all the way to the bottom of the tree along the longest path. So the while loop will execute as many times as the height of the tree. Since each iteration we're going one level deeper in the tree, by moving either to the left or to the right. And we're doing all of one work each iteration. We're doing some checks and then some assignment. Which means that the total work done by the while loop is O of h. And outside the while loop we just do a constant amount of work. So the time complexity of this function is O of h. If the binary search tree is balanced, this is O of log n. Let's analyze the space complexity of this function. Because we're using a constant amount of space, the space complexity is simply O of 1. You can find the link to the code in the description below. If you have any questions or comments, leave them in the comment section below.